Hello, everyone, and welcome to Unit 8, Day 1. So today what we're going to do is we're going to get started on our next topic. If you haven't already done so, please make sure you go back and watch the Zoom meeting because that's going to help set up this topic. It'll help it just give you a little bit of reference, so you know where we've been, where we're going kind of stuff. So assuming you've already done that, actually the first thing I want you to do real quick is I'd like you to update your table of contents in your notebook. This is just going to give that little layer of organization. Not so important right now, but the longer you use this notebook, or if you look at this notebook a long time from now, that table of contents is going to be useful. So the first unit for this trimester, or if you're continuing on from Chem A, was, it started on March 30th, went till April 10th, and it was Unit 7 on light. Okay, so with that little piece of logistics organization taken care of, let's get into our topic for today, Unit 8. What you're going to be able to do today is to describe and explain the periodic trends of atomic size, ionization energy, and electronegativity. So some new vocab words possibly there, and it's kind of a big deal. This is a big, big topic. This is something that chemists get really excited about. So as chemists, I'm going to be able to explain some really cool things about the periodic table with you today. So go ahead and set up your EQ so that you've got an idea of what you should be able to do by the time you're done. It'll help you write your summary. It will help you review, help you get going. All right, so you should be able to describe and explain the periodic trends of atomic size, ionization energy, and electronegativity. Let's get into it. So first I want to just take you back a little bit to where we ended up with this modern periodic table. The modern periodic table is based on the work of Cliffhanger. You're going to find out who were the important players in coming up with the modern periodic table by doing the unit reading for this unit. So from Schoology, you will download and then put into Notability the Day 1 periodic table reading, and that's going to give you a little bit of the history of the periodic table. So you're going to do that on your own. It's going to give you a little bit of history. There's some cool stories in there related to history too, not just stuff about the periodic table. So there's some interesting things in there that you'll note all leading up to the modern periodic table. So assuming you've done that, let's get into some of the ways we describe the periodic table. So first of all, I want you to be aware that periods on the periodic table are the rows. So though they go from left to right, there's patterns. This is where we don't see as many patterns. Things are really different as you go from one period or one spot to the next spot. So you get different physical and chemical properties as you go across the rows. And that's important to kind of realize. So different rows on the periodic table have lots of different properties between them, and then that's why they're in different rows. The columns on the periodic table are known as groups or sometimes families. So these are the 18 different vertical columns. So it's shown in like the different kind of colors there. And then this one, when you have a column, you have similar physical and chemical properties. So all of the elements in this column would have something in common. All of the elements in this column have something in common, making them group together or be related, a family. So that's where that comes from. I want to review a few special groups that we sometimes refer to so that you are aware of them if you hear them. Like, for example, you maybe remember the first group is known as the alkali metals. It doesn't actually involve hydrogen, but all the others underneath it, the alkali metals. And then the second group, which has two more letters in it, is known as the alkaline earth metal. So it's the element that starts with beryllium, or group that starts with beryllium and goes down. And then we don't really have special names for these, but then the other special name I want you to be aware of is the halogen group, which is group 17, and then also the noble gases, which we refer to the noble gases a lot. And the thing that makes the noble gases special that I can now explain to you, which I've never been able to refer to before, it's because their S and their P sublevels are filled. And so this is why they are noble and they don't want to interact with other groups, because they're already full. There's not a spot for them to put electrons into in their S and P out levels, and then there's no reason for them to lose anything because they're already considered stable. And so that's another layer of information that I was never able to use before when we talked about the noble gases, but now that you know electron configurations, the S and the P sublevels, that means something to you. So those are some of the sort of general organization pieces that we use when we talk about the periodic table. Would you please go ahead and do a level 1 question already? Something really basic, maybe something about periods or groups, maybe something about, special groups. But a level 1 question, go ahead and pause the video, do that, or come back to it later. All right, welcome back. what I have for you quickly is just a little side note related to the periodic table and then connecting to our last unit on electron configurations. So if you have a general periodic table that looks like this, the biggest reason it's organized this way is because of sublevels. So the sublevel S is called the S block on the periodic table, and it's these two columns plus helium. And what this means is the reason there's only two groups is because the S sublevel can only hold 2 electrons. And so the energy level is related to the row number. So like if I wanted to do the electron configuration for lithium, it would be 1, because the first row is 1, S2, because you're filling 2 elements in the first level, and then it would be the second level, and it would be S, 2S1. So 1S2 and 2S1. So here's the cool thing. You don't need that off-bow diagram with the arrows and stuff anymore. You're going to be able to figure it out from the periodic table. The P block, the energy level also equals the row number. And it's all of these, 1, 2, 3, 4, 5, 6, because you can have 6 electrons in the P sublevel. So if I wanted to do the electron configuration for silicon, I would say, okay, I fill up 1S2, 2S2, 2P6, because there's 6 across, 3S2, because it's the third row, so energy level and row are the same, 3S2, and then 3P12, so 3P2. So using the periodic table to write electron configurations, that's kind of the pattern. In the D block, remember that it's easier to fill S sublevels before D sublevels, and so that case, it's row number -1. So this whole thing, 10 across, this is known as the D block. So if I wanted to write the electron configuration for niobium, element 41, I go all the way back to the beginning and I would fill 1S2, and then I'd fill 2S2, 2P6, 3S2, because now I'm in the third row S block, and then 3P6, because I'm in the third row P block, 4S2. But then now, before I can go to 4P, I have to fill 3D, because it's row number -1. So I'm in the fourth level, 3D, and 3D10. Now I go back to the P block, which is 4. It's the same as the row number, so 4P6, and then 5S2, and then now I go back to row number -1, D block, 4D1, 2, 3. So then that would bring me to 41 electrons, and that would match my periodic table and my electron configuration. If I had an element down in the F block, I would take row number -2, because it's really difficult to fill all of this this F block before I fill some of these other ones. And this is row number -2. So if I wanted to fill neodymium, right, which is one of these elements here. So what I would have to do is I would have to fill elements 1 through 59, because really, remember, this should be like right here. So I don't fill up the rest of this D block level. I would stop at element 60. So that would look like this. Okay, go back to the beginning. 1S2 fills, 2S2, 2P6, 3S2, 3P6, 4S2, 3D10, 4P6, 5S2, 4D10, 5P6. Remember, I'm going all the way to neodymium, 60. So what was I at? 5P6, 6S2, and here's where it gets a little bit weird. So before I can fill up and get to this D block, I'm going down to the F block. So it goes 6S2, and then it goes 4F1, 2, 3. And that would give me my 60 electrons. So this is a way, and then here's just my energy levels and row numbers on the periodic table, just so that you can easily see them. So this is a way to connect electron configurations and the periodic table. There is a guide, this slide in Schoology to put in Notability, just to kind of help you for future reference. It's not something I'm going to make you do right now, but for future reference, using the periodic table to write electron configurations, one, it's way faster and actually a little bit simpler once you get used to it, instead of having to use that off-bow diagram with the arrows. So that's just a little side note I wanted to take you through, but it fits this unit where we're really focusing on the periodic table. All right, now let's get into it. So the meat of today's lesson is about using the periodic table to explain stuff about chemistry, so using the different trends. So the first thing I just want you to be aware of is that when you put the elements in order of their increasing atomic number, this is when you start to see patterns. So it's important to note that the periodic table is in order by atomic number. not atomic mass, not the number of electrons, but specifically the atomic number, which is the number of protons. And when you do that, you also start to get these different blocks on the periodic table, that this periodic table is arranged by their actual electrons filling. So you've got that F block shoved in here where it's really supposed to be, just to kind of give you this idea of what the periodic table would look like if we had more room on a page. So this is the periodic law. So all the trends we're going to talk about are based on the fact that the elements are arranged by atomic number. That is key. Before I even start explaining the different trends, I really want you to think about the nucleus, because pretty much everything in the trends are explained by the nucleus. So keep this in mind. The protons are considered big compared to the electrons. So both of them obviously are tiny subatomic particles, but if you compare a proton to an electron, a proton is considered big. And most of the trends are explained by how positive is your nucleus to overcome the negative energy of your electrons. So the positive power of the nucleus is really what we're going to focus on. And how does that interact with the electron cloud? So the electron cloud is negative. So if we think of the Wicked Witch of the West as your electron, your negative electron, and your big, powerful Glinda, just being silly here. But the idea is that it's the positive power of the nucleus. How does it interact with the electron cloud? That is going to explain all of our trends for today. So keep that in mind. The first trend I want to talk about is called atomic size or atomic radius, which is like the mother trend, meaning that it is the leader and it gives birth to all the other trends and really helps you explain anything else by thinking about this. The size of an atom depends on how much of a shielding effect there is. And here's what this means. When you have a nucleus in the center of an atom and you've got different energy levels, when there's more energy levels around that nucleus, the effect of that positive attraction is less. It acts like a shield. Those energy levels are blocking the power of the nucleus to pull the outer electrons in. So it's shielding it. That's why it's called that. So if there's more energy levels, they shield the positive attraction of the nucleus and it doesn't pull on those negative electrons as much. So then those electrons don't feel the attraction as much, which means that if you are trying to pull the electron cloud in, it's not as effective. But if you're adding electrons in the same level, so for example, as you go across a row for a periodic table, you're not adding energy levels, you're adding electrons in the same level, but you're also adding protons, so the nucleus is more powerful. So in this case, when you go across a row, the nucleus gets much more powerful, but there's not any more difference of shielding. So actually the nucleus is way more effective as you go across. So with that in mind, that brings us to what is the actual trend. So group trend, so up and down, the size increases as the atomic number increases, which means as you go down the group, the atom gets bigger. The periodic trend is as you increase atomic number, which really means from left to right, the size decreases. And that is based on shielding, like we just talked about. How powerful is that nucleus? Well, as you go down the group, there's more energy levels. That shields the power of the nucleus, so the nucleus is not as powerful, so the electron cloud can spread out. The atom gets bigger. But as you go from left to right, you are adding protons. You're also adding electrons, but they're adding in the same energy levels, so the shielding hasn't changed, but the nucleus is getting more and more powerful, so that nucleus can shrink or pull or attract the electron cloud in even tighter, so it makes it smaller. So that is what we're going to use, big or small atoms, to explain pretty much that's the most important thing to explain the other two trends we're going to focus on today. So go ahead and kind of process that for a little bit. Pause and do a level 2 question. Maybe something related to shielding or atomic size. Compare and contrast. Why would lithium be a smaller atom than cesium? That would be a great level 2 kind of question. Or why would sulfur be a smaller atom than aluminum? Those would be good kinds of things to think about. All right, welcome back. Let's continue on. The next thing I want to talk about is ionization energy. And ionization energy is how much energy is needed to pull an electron away from an atom. So if this case, high ionization energy, this atom is saying, no, my electrons are mine, you can't touch them. A low ionization energy is saying, sure, whatever, go ahead, take my electrons. I'm not holding them very tightly. The group trend is that the ionization energy decreases as you increase the atomic number, meaning go down a group. Well, think about what we just learned. Those atoms are bigger, which means there's more shielding, which means the nucleus isn't as strong or as effective, so it's easier, less energy needed to remove an electron. But for the periodic trend, it increases as you go left to right, increase with atomic number. So as you go this direction on the periodic table, remember, powerful nucleus, right? On the right side of the periodic table, the nucleus is more powerful. It pulls the electrons in tighter, which means it's going to be harder to remove an electron. So again, thinking about that positive power of the nucleus almost always helps you explain why a pattern exists. So then this would explain why certain elements are more likely to lose or gain electrons. It has to do with the power of their nucleus, the size of the atom. That's ionization energy. The last trend I want to talk about is electronegativity. This is how likely, or what is the tendency of an atom to attract an electron to itself in order to bond with another element. So here's a visual, right? So here's an electron or an atom. This is an atom. And how likely is it to pull these electrons towards it? So it's the opposite of ionization energy. Ionization energy is how much energy do I need if I'm over here to take these electrons away? Electronegativity is here's an electron, or here's an element trying to pull electrons to itself. That's electronegativity. Here's another visual. So imagine that this is an element and it is just hanging out and it's got its own electrons. If this element tries to come to this electron and try to take this electron to join itself and make a bond, look at how far away this proton positive nucleus is from this electron. It's going to be pretty hard for this nucleus to attract this electron because there's just so much space. But if this element tries to attract this electron, at least compared to this one, this nucleus is closer to this electron, which means it's more likely to pull it over, meaning this element would have a higher electronegativity and this element would have a lower electronegativity. This element is less likely to bond to this element than this one is because this can get closer, it can attract it stronger, and it's more likely to pull it over. So again, it's about the effective power of the positive nucleus. This nucleus is not close enough to be effective. This nucleus is close enough, so it's more likely to pull this electron to itself and to create a bond. Here's just kind of a little cartoon example. So here's oxygen, which has one level of shielding. Here's sulfur, which has two levels of shielding between the nucleus and the outer electrons. So because this has less shielding and the nucleus can get closer to another atom, this element would have a higher electronegativity. This nucleus cannot get as close to another element, meaning its electronegativity would be a little bit lower. So back to that definition, electronegativity is the tendency of an atom to pull an electron to itself, to attract an electron to itself. And there's numbers associated with thinking about what the number is of how likely it is to be electronegative. And it's named after this guy named Linus Pauling, who thought about something called electron affinity, like how likely are the electrons to change their energy, and on ionization energy. And so it's an arbitrary scale from 0 to 4, but it is based on real chemistry. And this is the trend. The tendency of an atom to attract an electron decreases as you go down a group, increase the atomic number. So the elements on the bottom are less likely to attract an electron. So they would have a lower electronegativity value from 0 to 4. And then the periodic trend, the tendency to attract an electron, the electronegativity increases as you go from left to right, increase the atomic number. So on the right side of the periodic table in a row, they are more likely. And again, it goes back to the power of the nucleus. The electrons on the right side of the periodic table, those elements, have a more effective nucleus, which means they're more likely to pull an electron from somewhere else because the nucleus is more powerful. The electrons on the bottom of the the elements on the bottom of the periodic table have so much shielding, the nucleus power is not very effective, so it's less likely that those elements could actually pull in an electron from another place. Go ahead and do a level 3 question. That was a lot of information to process. So go ahead and think about a level 3. So maybe which element is, or which periodic trend is the most important for bonding, or make a hypothesis about reason why two things would bond with each other based on electronegativity or something like that. All right, here is a summary. Sorry, apologize, let me go back. Here's a summary of the trends that we just did. So for your summary in your notes today, go ahead and do a quick sketch of a periodic table. And in general, the size decreases this way, but ionization energy increases and electronegativity increases, all because the elements on the right side of the periodic table have a more powerful nucleus. But atomic radius is bigger on the bottom, ionization energy is lower, and electronegativity is lower on the bottom because these elements on the bottom have more shielding, a less effective, powerful nucleus. So that's kind of the summary of today. And then that brings us to the end of day 1 of Unit 8. So here's what I want you to do. If you didn't do it already, make a Unit 8 Notability folder, put the Unit 8 plan in Notability, which then makes you look at the Unit 8 plan so you can kind of see what you need to know for this unit, what objectives are important, what assignments you need to do today. You should go back and do the reading from Schoology, the day 1 periodic table reading. So put it in Notability and then read it. And it also asks you to kind of summarize the timeline of a periodic table history. You could also finish your cost of questions and your summary from today if you didn't already do that. And then I would like you to do the unit practice problems. I don't have any other worksheet or homework for you to do tonight. So those unit practice problems, there's not very many. This is a great way to process. You looked at the notes, you listened to the notes, but did they actually make sense? That will be useful if you do those unit practice problems. Remember, they go in the back section of your notebook. Just kind of process and think through today's notes. And then I will see you at our next Zoom meeting. Let me know if you have questions. Of course, you can come to office hours or send me messages to see if today's new information made sense. Our next session, so day 2 for Unit 8, we're going to practice all of this. So as long as today's information kind of made sense, do the practice problems to see for sure. But then we're going to practice this for all of day 2. All right, thanks so much for joining in. We'll see you next time.